Okay, in this section of Chapter 8, we're going to look at internal forces in just a straight beam. So this really concentrates only on beams themselves, and we're going to look at straight beams in 2 dimensions only throughout the rest of this chapter. Again, what we want to do is be able to find this shear, moment, and normal force everywhere within this straight beam. So we're going to draw essentially shear and moment diagrams so we know what the shear and moment is everywhere within the beam, excuse me, and we're going to look at it as a function of x. In section 8.3, we're going to deal with it if we only want to know what this is without knowing what these functions are as a position of x. So the method that we do in solving these internal forces is essentially take a cut like we did in section 8.1. At some arbitrary location, we draw the free-body diagram, and we determine again our shear, moment, and normal forces for that free-body diagram. And they're always valid, essentially, as long as our free-body diagram is valid, and we continue to take additional cuts. Now, while this says arbitrary, there are specific areas that we're kind of looking at. Typically, when we see changes in forces, either external forces or reaction forces, we kind of want to know what's happening on either side of those changes. So while it's arbitrary, it can be arbitrary within those ranges typically, but we want to kind of know what's happening at those locations. So when we do this, we want to, again, know what these values are throughout the whole length of the beam. It's very important for us to set up some coordinate system. Typically, 90% of the time, it will be the left-hand side of the beam itself, and we will do a positive x going to the right. This will be a positive x direction for our beam. The other thing that we want to do is look at our shear, normal, and moment forces and come up with some sign convention. So I kind of blew it up here so you can kind of see it a little better. This is what we would consider as our positive sign convention. So if we cut a beam with this coordinate system shown here, our shear force, again, going down on the left-hand side of the beam is considered for our positive sign convention. Our shear on the right-hand side is going up. Our moment, again, is one in which we will say causes a smile in the beam on the either side, right? So it's a positive direction for that. That's our positive sign convention. And our normal is always showing away from that cut surface. The other thing is that positive load distributions are considered in the negative y direction. So what is drawn here, that's considered to be positive. Okay, so here's an example that I want to run through here, and then I have additional examples for you to look at. With this example, we're looking at a simply supported beam with a pin at A and a roller at C. We know how to solve for those reactions real easily. I'm just giving them to you right here. We aren't going to go through all of that. Below this beam, and I like to line up my beam with this axis for the shear diagram and the moment diagram. You'll see also that I have lined up these lighter lines which correspond with any changes or forces that I may see in the beam, and then also my end of my beam. And I keep everything lined up and one underneath each other just because it makes it easier for us to visualize what's going on and if our solution is correct. Okay, so the first thing that we want to do is make a cut. And we know, again, this AY is 400 newtons and CY is 600 newtons. And P, we are told, is pounds. 1,000 pounds. What we want to do is make a cut. And again, it can be arbitrary, but we want to make it before B as a cut, right? We want to, while it's arbitrary, it can be anywhere in this location at X, right? So if we look at that, we will then draw our free body diagram for that cut. Okay, you can see I've drawn our first free body diagram. One thing to point out, the problem also states that A is 6 feet and B is 4 feet. So I'm making this cut between 0 and 6 feet. So I label that for this section. I've drawn my free body diagram for it with my 400 pound reaction force, my shear force at 1, my normal force, and my moment force at 1. And it's at some random location, X. Okay, so now we can solve this free body diagram very easily. And if we look at it, we can sum forces in the X direction, of course, and we will find that N equals 0. And that's typically the case for this, and will be throughout this whole beam. And that's why we typically only look at our shear and moment diagram. If we look at summing forces in the Y direction, we have that equal to 0. We have a positive 400 minus V1. V1 then equals 400 pounds. Last, we are going to sum moments, and I'll do that at our cut 1, and that equals 0. And if we look at that, we have 400 minus 400 pounds times X plus M1. M1 equals 400 pounds times X. Okay, so now we have to graph this. And if we look at this, our range again is between 0 and 6 feet. We know that for our shear itself, it is 400 pounds positive, and it stays that the whole way through this up to this 6 feet. I'll label that as 400 pounds. And then our moment, we know at X equals 0, our moment is equal to 0. At X equal to 6 feet, our moment is equal to 2,400 foot-pounds. And we can now draw that on here. And it will be a linear equation. And this is our 2,400 foot-pounds. Okay, now we want to take another cut. We're going to take a cut at cut 2. This is our second cut, and this is at some other location, again, X. It's always relative to our origin, or 0, 0. So let's look at cut 2. I'm going to draw the free body diagram over here on the side for us. Okay, so here's our free body diagram for this cut. It's out, again, between 6 feet and 10 feet. The last thing we want to know is what is this distance between here and the end. And that, of course, is X minus 6 feet, right? That's that distance here. Okay, now we have all the information we need to solve this. Again, we are going to look to find our N1, N2, V2, and M2, our normal shear and axial load. If we sum moments, or sum forces, in the X direction, and I should have the X-axis on here, we find that our N2 is equal to 0. If I sum forces in the Y direction, set that equal to 0, I have plus 400 minus 1,000 pounds minus V2. We find out that V2 equals a minus 600 pounds. Last is to do a moment, and let's take a moment and some moments at 2 again. Our cut is where I'm going to do it. If I have that, I have the 400 pounds making a negative moment, 400 times X. I have the 100 pounds, or 1,000 pounds, times X minus 6. causing the moment around this N2 cut, plus M2. We can now solve for M2. Okay, so we have our equation for our moment right here. From this, we can then solve for at x, again, equal to 6 feet. We will find that M2 is equal to 2,400 foot-pounds. And at x equal to 10 feet, we find that M2 equals 0 foot-pounds. Okay, that corresponds to the end of the beam. And if we look at this, what this looks like on our drawing is right at B, we have a discontinuity which jumps down to a minus 600. This is minus 600. And then we see that this is at 2,400 and comes down nicely to 0, which is kind of nice because we know there are no moments at pins or rollers. We see that there is no internal moment at those locations either. Okay, I want to look at one other short, quick example. I'm not going to go through the math on solving all of this, but essentially what I have here is I've got two distributed loads, or two loading situations, one with a distributed load and one with a point load. And we know if I work this out on the part A, that if I rewrote that with a point load, that this is P is equal to our W naught L, right? That's what we would have. And essentially these are two equivalent force systems for us. So while they're equivalent force systems, the question really is, are the shear and moment the same for both of these types of loading? So what are the internal forces to these two different systems? Even though while they are equivalent by their external loading, what does the internal loading look like? To find that out, we would need to draw a shear and moment diagram and compare the two. And I'm not going to go through the math of it. I'm just going to show you those. So you can see from this diagram that the loadings are significantly different between the two of them. And what we see here, and is very important, is this concentrated loading over here actually has caused a moment to be twice as much as the moment in the distributed loading. So that's a significant part. The other is that we have this discontinuity that happens here. It's a real abrupt change in our shear force also. So the big takeaway from this is that even though we have two loadings that are equivalent systems, our shear and moment are very different from each other. So our internal forces are very different. And again, like I pointed out, the moment is twice as high for our concentrated load as opposed to our distributed load. So again, to summarize this one last time, you can have two force systems that are equivalent and they produce the same external effects, but really the internal effects of these are not necessarily the same.